And we're really happy to have him here today. So Pierre, the stage is yours.
Thank you very much. If I talk like that without a microphone, is that okay for the people in the back?
No, you need because of the cameras and the recording.
Okay, maybe that's...
Just press the unmute, this one.
Oh.
Now it will.
Yeah. It's better for the back? Yeah. Okay, thank you. No, I go backward. Okay, yeah. So today, after those three presentations from this morning and before me, that were very interesting on how to actually assess the structure, the tunnels. Now I would like to go one step further and show you what we do when the decision has been taken to do the refurbishment or the restoration of tunnels. Okay, and I want to show you results we did last year in the Czech Republic, where the solution proposed by SIKA and the engineers was awarded a national award for the work they did there. And at the end, I would like to present to you what SIKA is believing is the future in the waterproofing of tunnels. So for this project in the Czech Republic, it is on the main line north-south between Prague and Brno. And we are looking at just north of Brno, between Blansko and Brno, where there is roughly 20 or 30 kilometers. And there, 9 tunnels were refurbished last year. And we will divide those tunnels into parts. The first part is between Blansko and Adamov, and then between Adamov and Brno. So if we look at the tunnels from Adamov to Blansko, all those tunnels were built in the middle of the 19th century, in 1848. So they are older than all the tunnels we have heard about this morning and this afternoon. And they were built roughly less than 10 years after the first train arrived in the Czech Republic from Vienna. The first line was between Vienna and Brno, and then they started to build the line between Brno and Prague. And it's on this line that those tunnels have been built in 1848. We see that the tunnel, there is tunnel 8.1 and 8.2. Of course, those tunnels since 1848 has been refurbished a few times already, and especially in 1992, when they started the electrification of the line. And for that purpose, they needed a bigger clearance for each train. And we see that the tunnel 8.1 is only one track. There is no space to have 2 tracks in the tunnel. So in 1992, they built a second parallel tunnel, the 8.2. Here we see, for instance, the tunnel, the cross-section of the tunnel number 7, where obviously there is not enough space to have the 2 trains crossing each other in a tunnel. It's still a 2-track tunnel, but the train cannot pass or cross each other in the tunnel itself, which is not a big deal because all of those tunnels are pretty short, right? We are not talking about big tunnels 10 kilometers long. So they are short tunnels, but the clearance is what it is, and we have to do with the requirements. That means also when we do the refurbishment, we need to find a solution that is as thin as possible, right? Because most of the time we do not remove the existing layers. We will try just to put an extra waterproofing layer that will do the job for many years to come. Oops. So the solution that has been used is to have a waterproofing membrane that goes from one side to the tunnel to the other side. We are not interested in this case to waterproof the whole cross section of the tunnel, right? This has been drained tunnel. That means that all the water that is collected in those tunnels are evacuated on the side with pipes. So we see here the system. We have the waterproofing membrane that goes all around the tunnel from one side to the other, and we have on each side the collecting, the pipe collecting the water. So the water stays between the external structure, the shotcrete, and is diverted into those collecting pipes and evacuated out of the tunnel. So we need to waterproof from here all the way around the tunnel, okay? And we are using a membrane made of PVC in this case. So it's PVC-based membrane. It's 2 millimeter thick, right? And we finish with a layer of shotcrete to protect this waterproofing membrane. Here we see the tunnel 8-1, the one which is only one truck. We see that obviously there was no space to put two trucks in this tunnel, and it's a different construction. It's a masonry, stone masonry construction plus a shotcrete layer. And we just came on top of it with the membrane. Initially, the solution that was developed by the engineers were just to do some injection of material where the tunnels were leaking, right? So of course this solution would be economical and not take any space, reduce the clearance any less, or take any further space in the tunnel. But they started to do those injections in spring, and they were satisfied. In summer, nothing happened. But when came fall and winter, well, the rain came back and new infiltration appeared in those tunnels. So very quickly they realized that something more needed to be done. And we worked with them, with the engineers, with the specifiers, and we came up with this umbrella solution where, like I described before, we will just collect the water on the side of the tunnel to keep everything watertight for the electrification line and the trains. Then we have also to refurbish the portals, and if we have the membrane inside the tunnel, we need to be able to finish it, to terminate the waterproofing at the portals. So the way to do it, the membrane cannot be fixed directly onto the concrete. There is no easy fixation directly of the membrane onto the concrete unless we use a clamping system, but the clamping system is a very expensive system. So we have developed a tape here that we will just glue to the concrete using epoxy, right? So it's a tape that has been developed for that purpose, and on top of it, we can just come and weld the membrane onto it. So with this solution, we are able to guarantee a watertight solution for the entire length of the tunnel, including the terminations. So here we see the tunnel 8-1, the old tunnel, 1848, and the new one, 1992. Okay, and on the other tunnel is a tunnel number 9. We see that during the renovation, here we are not doing the renovation at night like in the metro station on metro line. Here everything was stopped for the duration of the refurbishment because even the trucks were replaced at that time. And this is the National Railway Construction Award that was given to the refurbishment of those 4 tunnels. So the first thing to do is to replace or consolidate the invert where the tracks are laid. So with a mortar. Then we need to put a drainage layer behind the membrane all around. So this drainage layer is necessary because you need to guarantee the space for the water to drip down towards the collecting pipes. If you put the membrane directly on a very smooth surface and then you project or you cast your concrete against it, the pressure of the concrete or the shotcrete will push the membrane against the substrate, and you may not have enough space for the water to drip down towards the collecting pipe. So we put each time a drainage layer. This drainage layer has a geotextile attached to it to protect the membrane. The membrane is only 2 millimeter thick, so if the substrate, the shotcrete substrate for instance, or the concrete substrate has some asperities, and if with the pressure of the concrete or the shotcrete we plaque or we force the membrane against those asperities, we may damage the waterproofing layer. Okay, and so we put a geotextile just to protect the membrane before we can apply the shotcrete. So this drainage layer is fixed with some discs, right? They are just shot with nails through the shotcrete, right? And after that, we come with the rolls of membrane and we weld the membrane on those discs. Those discs are made of the same material as the membrane itself. We have 2 types of membrane for waterproofing tunnels or basement. It's either based on PVC or on TPO, right? So one is easy to weld, more flexible, that's the PVC, so much easier to work with. The other one, the TPO, is a little bit more expensive, it's a little bit more stiff, but has a better chemical resistance. So if your underground water has some harsh chemicals in it, we would use a TPO membrane, right? But in most of the cases, in 90% of all the tunnels waterproof with membrane, it's PVC we use. So here is once the membrane is applied in the tunnel, and here this is not a disease, it's not measles, okay? These are spacers that have been put in place in order when we put the reinforcement, the steel reinforcement for the shotcrete, right? We still have a gap between the membrane and the reinforcement, right? We don't want the rebars to have no cover, concrete cover, so we need to put spacers. So how do we put those spacers? Well, we need to make a hole through the membrane, right? So we put an accessory that we call an anchor, which is a hard PVC shaft with a membrane of the same type as the waterproofing membrane. So this is a one accessory that we will fix with epoxy inside the shotcrete. Then what we obtain after that, we weld again the accessory onto the membrane, and now we have recreated the water tightness of the system. Right? The water cannot enter this because it is a PVC structural element that goes inside the shotcrete. And then the water cannot come around this because it's fully welded. Right? So for that purpose, we use a chemical which is epoxy-based, thixotropic, and then we just screw the shaft inside the hole prepared. After that, we just put a threaded rod that we can screw inside the shaft, right? And then we put a spacer, like we see here. Then we can put the reinforcement mesh for the shotcrete. At the end, we have the structure like that, ready for shotcreting. The advantage of this solution with this anchor is that we can really then cut the threaded bar here, the threaded rod, and we will have no protrusion of the system. Okay? So this is a very nice solution for when we have a very tight space to put the shotcrete. We cannot just say, oh, I put as much shotcrete as I need to cover everything. No, we need to put as less shotcrete just to make sure we have enough to recreate the structural strengthening of the whole system of the tunnel. So then it's the shotcreting, regular shotcreting. Here's how it looks at the end before they put back the trucks in the tunnel. Then we put back the electrification line, we put back the trucks, and the job of the waterproofing is done. In the second set of tunnels between Adamo and Brno, we did not use the SIKA anchor as before. We just use what we call a trumpet flange. It's also a PVC element that looks like a trumpet. So there is a piece here, a tube with the base, and this time we put first the rod directly inside the shotcrete, or maybe even further inside the rock if necessary. So this allows, in the previous system, we were limited by the 30 centimeters of the length of the PVC shaft, right? Now, there is no more PVC going inside the shotcrete. It's just the rod. So we can fix the rod as far as we want or as we need. Right? If the shotcrete behind is not so strong, then we will drill further, go find the rock, and embed this threaded rod there, so we have enough pulling strength. And then we just fill this tube with some sealant, and we squeeze it, so to recreate also the water tightness. Here, again, we will weld the trumpet onto the PVC membrane, so the water cannot penetrate the system. But with this system, the disadvantage is that you have a bigger protrusion of the system. With the anchor, we were flush with the membrane. Here, you have at least 5 to 10 centimeters that you need to seal with the sealant the system. But in those tunnels, we had enough space. So there was, of course, the trumpet flange is much cheaper than the anchor system that we saw before. So here we use this system, and because we can go deeper inside the rock, we need less of them. That means at the end, we have less of those anchoring system in the tunnel. But it's the same principle later. We put the reinforcement mesh, and we can do the shotcreting to finish the system. Now, I'm done with the presentation of the refurbishment of the tunnels in the Czech Republic, and I would like to take a few minutes to present to you what we think is the future of the waterproofing in tunnels. Up to what you have seen now, it's a loose-laid membrane. That means that once you apply the membrane, then you put the concrete or the shotcrete against it, and there is no connection between the concrete and the membrane. That means if there is a problem with the waterproofing of the membrane, the water that penetrates through the membrane can travel between the concrete and the membrane. And once the concrete is cracked, you will find a place to come out. You will see it. You will say, oh, okay, I just have to inject this crack. You inject this crack, but you did not solve the problem, because the water will find another way, a little bit more complicated, but find another way and find another crack and come out somewhere else. Right? So this is an unending repair solution. SIKA is happy because SIKA also sells injection material, but we came up with a better solution, and the better solution for us is to use what we call a fully bonded membrane. That means this membrane has been modified for having what we call a bonding layer, that when you cast your concrete against that membrane, right, that create a bond, and the water cannot travel anymore. So the thing is, we will see. I'll show you how it works. In our solution, we included already the geotextile at the back of the membrane. So on one side, we have a bonding layer to bond to the concrete, and on the other side, on the back side, you have a geotextile which is already fixed to the membrane. So we are simplifying the way of the application of the whole waterproofing system. So we just nail now the geotextile to the shotcrete. We see here the waterproofing, the bonding layer, right? This is a concrete block, and this is a membrane. And when you pull the membrane out of the concrete, that's what you see. Okay, so it's really a rough structure that has been designed to fully bond to the concrete. And at the end, we have a much simpler waterproofing solution. It's the same thing, it's an umbrella, it's a drainage system, but we no need any water bars, for instance, if we want to create compartments and things like that. Because, again, the use of the water bars to create compartments is, if you have the membrane which is punctured, then the water will penetrate between the membrane and the concrete, the inner lining concrete, and find its way out through some control sockets that we will include in the system. And when this happens, we can always inject the compartment with some injection material that will recreate the waterproofing, right? But those compartments are made of water bars that are welded to the membrane, and when you cast the concrete, then the water bar creates the water tightness. So we confined the water problem into one compartment, roughly 100 to 150 square meter. We could have compartment much smaller, but it costs a lot of money because you have to weld water bars, you have to buy water bars, you have to weld them together. So the optimum size is roughly 150 square meter for those compartments until now. But now, because the water cannot travel anymore, we don't need those water bars anymore, right? So we really simplify the installation process. This is what we have until now. Like I said, we have the rock, the shotcrete, the drainage layer or the protection geotextile, the discs, the membrane that is welded to the discs, the water bars to create the compartments, and then the reinforcement, and then the inner lining concrete. Okay, so we see here, and this is how it looks for an umbrella system with the two pipes collecting the water behind the membrane. So the way to apply it, first we have to put the geotextile. Then we put the discs. We see the discs here. Then we weld the membrane onto the disc. We see there is one point here, one disc, one here, one here. So we have to do that step. And here that's a pictogram to explain how it happened if the thermoplastic membrane is punctured. The water will come in and will travel between the water bars, right, into the compartment. If you have a crack in your concrete here, the water will come out. If you inject, you close this crack, but there will be another one somewhere else, etc., etc. Right? So, but it's how it's done nowadays for those waterproofing of tunnels. And it's pretty complicated. Okay. So we see all the water bars. We see here the injection sockets with all the blue pipes that will be linked to an external box that is coming out of the inner lining concrete. So when there is a leak and the water enter, it will go to the socket through the pipe and come out. So we know we have a problem. So we can inject. So we will inject the material to fill up this compartment. Then that's fixed. That's the solution is okay. We have recreated the waterproofing by injecting later on some injection material. Okay. But it's pretty complicated and prone to failure or human problems if you don't do a proper job. Now, with our solution, we have the rock, the shotcrete, we have the geotextile which is attached to the membrane in the back. So we will just nail it, and then directly we can come with the concrete and the reinforcement if needed. Okay, no more water bars, right? Now we have a solution where we have in one product the geotextile, the thermoplastic membrane, and the functional layer to create the bond with the concrete. And in this case, the product, we have two different products. One which is called the SIKA Proof 200, which is a 2 millimeter thick TPO membrane. This one doesn't have the geotextile at the back, just the functional layer. Okay, but this is the closest we have to match the current standards. In no standards for tunnels nowadays, we talk about fully bonded membrane, right? That's what is the future, according to us, right? But in most of those standards, they require a minimum of 2 millimeter thick membrane if you go deep, right? So we have created a membrane which is 2 millimeter thick, but we think the future is not that. This is one step. The future is a 1 millimeter thick membrane only, right? We don't need the 2 millimeter thick anymore, because now we are bonding this membrane with the concrete. Okay? It's no more a loose system. It's really part of the inner lining concrete. Right? So we can allow to have a thinner membrane for the same end results. That means a watertight structure. Okay? And for as long as, what are the requirements? Nowadays, in some standards, we talk about 100 years for tunnels. Right? We need a waterproofing system that can last 100 years. So with our solution, even with a 1 millimeter thick, we can achieve those 100 years because it is, again, bonded to the concrete. And when we look at the whole system, we have something that can last as long as this. So we see here the detail of the membrane, where we have the membrane itself, we have the functional layer, the bonding layer with the concrete, and in the back we have the geotextile, which is only spot welded, not fully laminated, because if you fully laminate the geotextile at the back of your membrane, you modify the technical characteristics of your composite material. Right? So by having just spot fixing, we have enough fixation to hold the membrane in place, but later, if it's moving, we don't really care anymore of this bond between the geotextile and the membrane. Nothing can go anywhere. It's squeezed between the rock, the shotcrete, and the inner lining of the concrete. And for the installation purpose, we need an extra strip of geotextile in the middle, because this is a 2 meter wide roll. So the way to fix it on the top of your structure is you nail first this strip that holds the whole membrane and the geotextile, and then you go on the side and you nail it on this side and this side. Then you do the next one, and then you can do the welding between the membrane. That's the other thing. It is possible to weld a membrane with a functional layer. Okay. We are the only one who has such a membrane that is weldable even with a functional layer. Okay. And it's a big advantage. The others needs to use tapes, and we don't think that's the right solution to go in tunnels with tapes, right? Because the issue with the tunnel is, contrary to basement, you have a shotcrete substrate, which is not even, right? You have more or less to follow the rock blasting. That's why you put the shotcrete, is to create a better surface to apply the membrane, but this surface is not smooth like a concrete that has been cast in a formwork. Right? It's still undulating pretty much. So if you put the membrane and you put a tape, and after that you come with your cast-in concrete, the pressure of the concrete will push the membrane into those holes. And if you don't have a good bond between the two rolls of the membrane, then it will debond and the concrete will go behind between the two membranes. So this is not what we want. So we have created a membrane that we can weld, still weld, even if it's not a smooth surface like we are used to. But we use the same equipment, the same welding machines, and it works. So in a short note, what are the advantages and benefits of this system? Like we said, it's a fast and easy application. Okay, we reduce the installation steps from 4 to 1. Right? In one go, you apply the membrane with the geotextile, so you don't need to go one time with the geotextile first, then with the discs, then with the membrane, so and then with the water bars. Now we just go one time, you put everything in place and it's done. Then you can weld. It's simple but effective. We have much less accessories. Okay? We have no water stop needed. We have no injection system required, no compartments. And if we have a leak, which is always possible, right? If we have a leak of the membrane and your concrete, your inner lining concrete is good, has no crack right there, nobody will never know you have a leak. The water cannot travel, right? The water will go through the membrane and will be stopped by your good concrete. If we are unlucky and the membrane is punctured and there is a crack in your inner lining concrete, the water will seep in, but you know exactly where is the leak. It's right there by the crack of the concrete. So now you can inject your concrete to repair this crack, and you have solved the problem. The water will not find another way to find another crack, because, again, the water cannot travel between the membrane and the concrete. So it has to travel behind the membrane, but behind the membrane there is no other holes in the membrane, so that's it. You have solved the problem. So that means at the end you have less risks in your system. And it's reduced CO2 emission because we have a much thinner membrane, right? The production of a plastic membrane is costing in CO2 emissions. It's petrol, right? So somehow, if we can reduce just the thickness of that element, we reduce sensibly the amount of CO2 that we emit during the process. So here it's the normal loosely laid membrane where we have only the thermoplastic layer. And here we have what we call our functional layer, that is bonded to the thermoplastic layer. That's how I explain what happens if the membrane is punctured. This is a loosely laid system. The water can travel between the membrane and the concrete, find a crack, and come out. Now, the water punctures the membrane, punctures the functional layer, arrives here. But there is no crack here, no joint. The water stays here. Finished. If we are unlucky, like I said, we just inject the crack, and that's it. Here we see a microscopic picture of the system. We have the thermoplastic membrane here. We have our functional layer, and we have the concrete here. So we see that we have an interlocking of the concrete with the functional layer, but we also have a chemical bond between the functional layer and the concrete. So it's why we call an hybrid bonding layer. This is how the membrane functional layer looks like. And like we have seen this picture already, when you pull the two apart, that's what happens. This solution, because it's using a waterproofing membrane, plastic with good elongation, we have a very good crack bridging ability. This is nothing new. It's one of the advantages of the PVC or TPO membrane in waterproofing. It can bridge gaps quite well. And here we see we will never experience such gap in a tunnel construction, I hope, right? But it's still functioning. It's not breaking, even if we have 5 centimeters of elongation at one point. Right. So our solution, we saw a slide earlier where there was 16 points related to sustainability. So we have picked 3 that is related to this application, right? So basically, we have a responsible consumption and production because we have a simplified process. We reduce the membrane thickness. We have less products used in the system, waterproofing system overall. So we can reduce by roughly 40% of the material used compared to a traditional waterproofing system in tunnel. And it's also innovation and durable solution. We have a dual bond technology, high chemical resistance. Like I said, FPO, TPO is better in that regard than PVC. And we have a service life that is fulfilled. We will meet the life expectancy of 100, 120 years as expected nowadays in those underground structures. Oops. So again, here we see how it looks, the membrane. So again, the advantage is the application is much easier, right? We reduce the steps from 4 to 1. The geotextile is spot fixed only, so we don't modify the characteristics in itself of the waterproofing layer of the membrane. And we have added an extra strip of geotextile in the middle to ease the installation of the membrane. And in this case, the geotextile provide both protection of the membrane against the asperities of the shotcrete and also a drainage layer to let the water flow to the collecting pipes. And again, we don't need to use any water stops. This shows the difference between the two systems. The traditional system waterproofing, right? Either with a PVC or a TPO membrane, loosely laid. And here we have a surface modified membrane, and membrane itself is FPO or TPO. Okay. The bond to the lining concrete, in one case we have nothing. The other one we have the physical and chemical bond. The drainage protection layer. So here it is done in a separate step. It can be also done by using other sourcing of the material, while in our product everything is combined, so you know what you get for the whole system. No more water stops, installation steps easier, and normally, like I said, in a regular waterproofing work, you need a membrane 2 to 3 millimeter thick. Here we have only 1.4 millimeter, including the functional layer. The waterproofing membrane will be only 1 millimeter thick. Right. And in both cases, we use thermal jointing for the membrane. How do we test the water migration between the concrete and the membrane? There is an American test standards that we modify a little bit for our purpose, but the principle is you have a piece of concrete, you put your waterproofing membrane, and you make holes in your concrete. And then on top, you have a plate, this plate, and you put water under pressure. And once you just check after the test is done, up to 7 bars. You peel off the membrane from the concrete, and we dye the water in a certain color. Here's purple. So this is the concrete. You see that it is here. It is dyed. Sorry, that's the other way around. We make a hole. We make a hole also in the membrane. Right? We make a hole in the membrane here, and you see that the concrete is dyed, but the purple color doesn't migrate. Here we see the membrane. There is no water detected in the membrane. So we can go up to a depth of 70 meters or more. Just the test stopped at 7 bars. Right? Quick pictures. I know my time is up, but quick pictures of the application. The rolls are delivered on site. They are just unrolled and mounted on the gantry. Then fixed, like I said, first in the middle strip, then on the side, then welded with a regular welding machine, double seam. We see here, it's welded here, welded here. It's controlled like regular waterproofing job. Each weld is controlled, and then we can cast the concrete. We have the same type of accessories for the penetrations, either the anchor. This time we changed the waterproofing layer. It's the same type as the one for the SIKA proof, the fully bonded membrane. We can still use the trumpet, no change here, because it's weldable. So we can weld the TPO membrane trumpet onto the functional layer. Or we have also, if your shotcrete is very good quality, you don't even need to go 30 centimeters into it. You can just use an anchor bolt, right? And we have a system here that is the same principle, that you would weld on your membrane, and then you can just put whatever you need to hold the reinforcing mesh in place. Project references. This started in Korea more than almost 10 years ago, and we have big projects. One example here, we have 155,000 square meter for a tunnel, right? And this is how it looks before you cast the concrete. Okay, specification. That's it. Thank you very much.
Thank you, Pierre, for this detailed and very clear presentation. I saw some of the people taking photos. Now the general question, the presentations will probably be sent to all the participants, just making sure that you know, in case you could not take the photos. Any questions? We have a couple of minutes, and then we have something extra for the end. No questions in Slido so far. There is. Farid.
Hi, got a couple of questions. Thank you for your presentation. It's really good. So I've got 2 questions. One, which is on site, because you said it's going to be fully bonded. So I know you showed the testing that you probably did in a laboratory, but what tests would you have to do on site to demonstrate the quality and the bond?
You would not be able to do that, because once you put the membrane and then you cast your concrete, you have no more access to your membrane. So you cannot check after you cast your concrete how good the bond is between your membrane and the concrete. So this needs to be done beforehand if there is question about it.
Okay. And the second one is, we've used spray-applied membranes, which are also fully bonded. So what are the advantages of what this has over spray-applied membranes?
Okay, spray-applied membrane works well in a few conditions. First, you need to have a dry substrate, right? Here, you could use this system also when your substrate is not dry, and it's most of the cases that we know of. The second advantage of this system compared to a spray-applied is the control of the waterproofing layer thickness. When you spray-apply, as its name implies, you spray it. So how do you I return the question to you, how do you check the thickness of your spray-applied membrane, right? You know your consumption. If you know your consumption, you know that you have to put so many kg per square meter, and you assume that in average you have enough. But what does it mean, right? If you have asperities of your shotcrete, and if your nozzle man is not good enough to go all around those asperities, you are not potentially creating a full waterproofing layer using a spray-applied membrane. Here, you have a guarantee that you have 1 millimeter of waterproofing layer that has been created in a factory under controlled environment, the same as a loosely laid membrane. So this is something that you control permanently. So that's an advantage compared to a spray-applied membrane.
Right. Thank you. One or two more questions. There's one from Marco, and another one there. So first Marco, and then in the third row.
Thank you, Pierre. Hi. General question for bonded membranes. You've shown the accessories to fix into the substrate without damaging and ensuring that you have continuity of the reinforcement. And did you have to do anything in particular for the overhead line fixings? Did they have to be installed beforehand? Or in general, if something wasn't planned for and you need to fix and penetrate the bonded membrane, how do you normally address in that case?
Well, if your diameter of your anchor or rebars need to fix through the membrane is not too big, and we can use, for instance, the trumpet flange, you can drill through the membrane. You can drill through the membrane, you put your anchor, your fixation, and then you put the trumpet flange, and you can weld it and squeeze the sealant, and you have recreated the waterproofing system. Right? Once your diameter is much bigger, then you have to create an element out of the membrane itself that you can shape on the side of going around. You recreate a trumpet flange, but on site on a bigger scale. But it's the same principle. You would create it, you will weld it to the membrane, and you will squeeze it so that there is no water that can go through.
Thank you.
Yeah, maybe just two questions. One is regarding production, because yeah, it's clear that we have one step compared to 4 steps. I don't know if you have some data, even in percentage, if you don't talk about, I don't know, square meter done 4 hours and so on. Also in percentage, how is performing the system compared to a traditional one that you showed. And the second one is also that I see the list of tunnels. So now the system is in place for a few years in different projects. If you have some feedback on performance of the system compared to tunnels in similar conditions.
Okay, I'll answer the second question first. 10 years is nothing in the tunnel history, right? So if your concrete, inner lining concrete has defects after 10 years, you have to be worried about your whole tunnel, right? So no, we have no negative feedback so far of the system, but I have to say also, we have no negative feedback of a regular compartmented tunnel system, right? The only thing is with all those systems, like I said before, once you have cast your concrete, you have no more access to the waterproofing layer, right? So if you did it wrong from the start, you will know it quickly, but you are in a big mess. You have to remove the concrete and you have to restart, right? It's why we create those compartments, try to minimize our risk. If the membrane is punctured for whatever reason, you know, when you work on a tunnel, you put your membrane, then the next step is to put the reinforcement in most cases. Those reinforcement rebars are huge, heavy. You work in a confined space. Human error is possible. You carry a rebar, you have to put it in place, you turn around, you scratch the membrane. Okay, we have addressed that and say that we have a very thin layer of membrane in different color, so theoretically you should see it, right? But I can bet you, if one worker does something like that, the first thing he will look, he says, oh, I don't see anything, he will not say nothing, right? I continue my job, right? The quality control comes and says, hey, what's that? It will be nobody's job, right? Nobody's fault. But these things happen, right? So that's why we created the signal layer, the thin signal layer. And now it's also why we created the compartments, because we want to be able to repair in case something like that happens. But now with the fully bonded membrane, we don't have this fear anymore. That's, of course, it's also two different colors. Our membrane is black, and the functional layer is light gray or white, right? So, but it's not the same signal that if it was a very thin layer of membrane, right, less than 0.2 millimeter, that is bonded to the waterproofing layer. This is more difficult to check because it's rough structure. So you really need to damage a lot in order to see that, oh, it's no more gray, it's black, right? But again, it's less risky because behind this scratch, most likely, or in front of this scratch, now the concrete is good quality. So if it's punctured, the water will come against your concrete, but it will not travel anywhere.
Yeah, let's say the point for this is mostly that these were really like a really clean construction site, all the images and everything. They say that a lot of time, especially when you perform the joints with the invert side, sometimes the construction site can be really muddy, or you can have a lot of different conditions. So the connection is not so easy to be clean, and the concrete probably in reality will not be of good properties in the end. And so if you have also dealt with some condition like this, let's say more unfavorable condition, and if you saw some differences between the two systems.
In both systems, the issue is the welding.
Because in the first case, they generally are not working. If the concrete is not good, and then the connection cannot be good, then they are not working well.
Yep.
And I just want to make sure that we need to sort of close, so shorter answers because we have one more waiting there.
Yeah.
So.
It's clear that the membrane must be dry when we weld it, and must be more or less clean, right? If you keep your rolls of membrane in a dirty place or under the rain, first you have to let it dry, right? And if it's really muddy, you have to clean it with water first, and then you let it dry, right? So, but the bond is good after that. Yeah.
Thank you.
All right, now a quick one, and then we'll wrap it up.
Does it work?
Yeah.
Can you hear me? Super. Thanks for the very interesting presentation, Mr. Favre. You were mentioning that it's actually double bonded membrane, but that's because there is a mechanical and chemical bonding, if I understood well. So my question is actually how the chemical bonding is activated in your system, just to understand.
It's because in the functional layer itself we have cement, right? So when cement come into contact with fresh concrete, there is water, so there is enough, there's all the chemicals required to create this chemical bond, right? Cement.
Cement-based layer, which is
Yeah.
activated by the moisture, actually.
Yes.
The moisture. Okay. Thank you very much.
Welcome.
All right. Thank you, Pierre Favre.